Good morning, dear colleagues. Today we're presenting you a result of the research in the topic Programming the Formation of Difference Color Models for Lossless Image Compression. In this study, we propose a method and a corresponding algorithm for selecting adaptive difference color models with integer coefficients for improving the efficiency of progressive lossless image compression. To speed up the output of large images in compression formats with LUTs, graphic formats that use progressive hierarchical pixel processing have already been developed. This approach allows you to stop decoding after the compression of the layer with a number of pixels not less than the output or area on each of the axes without waiting for the reproduction of all the pixels of the image. Encoding pixels of the images in common graphic formats that perform lossless compression is most often performed sequentially, in lines from top to bottom and in each line in a row from left to right. Therefore, it's possible to display a compressed image in these formats only after decoding of all the pixels. The goal of the research is developing the HBF-LS format for progressive hierarchical lossless image compression, which will allow quickly obtaining reduced copies of the image without decoding the entire file. In this article, we propose a method and a corresponding algorithm for increasing code redundancy by reducing inter-element redundancy using adaptive difference color models with integer coefficients in the process of such compression. Any data compression is possible due to the reduction or elimination of redundancies. Three main types of redundancies are distinguished in images. Visual, consisting in the presence of information that is not perceived by the human visual system. Inter-element or spatial, manifested in the correlation of brightnesses of adjacent pixels. Coded, revealed when using codes of the same length for elements with different probabilities. It's common knowledge that the more types of redundancies of each type are processed by the graphic format, the more effective the compression is. But in the process of lossless compression, information is not lost. That's why the first type of redundancy is not reduced. Therefore, lossless image compression in archivers or graphic formats most often contains four main stages: compression by context-dependent algorithm, the transition to an alternative color model, usage of predictors, compression by a context-independent algorithm. It's extremely important to remember the basic principle of context-independent coding. Elements with a higher probability should be encoded with sequences of bits of shorter length than the cutoff lengths of elements with a lower probability. According to the fundamental position of information theory, to minimize the length of the sequence code, the element brightness with the probability of p should be encoded with logarithm of p to the base of 2 bits. Therefore, the average code length of the block element after the application of any context-independent algorithm, according to Shannon's formula, cannot be less than the entropy of the source. As a result, the entropy of the source decreases with increasing non-uniformity of the distribution of probabilities between the elements. And our main goal is to increase the non-uniformity of frequencies using difference color models with integer coefficients. As an alternative to sequential pixel traversal, we propose a progressive hierarchical traversal by which on the first layer we must consistently bypass pixels of the image beginning with the first on lines from top to bottom and in each line in a row from left to right with a step 2 power of k, where k is determined from the condition that you can see on the screen. On the next layers from 2 to k plus 1, intermediate pixels of the image are processed in two passes. On the first pass, those of them which are contained on the crossing of diagonals of squares with vertices in adjacent pixels of the previous layer. And on the second, unprocessed pixels are processed between adjacent pixels of the previous layer and the first pass with the same step on columns and with twice reduced on lines. Schematically, the sequence of hierarchical traversal is shown in this diagram. Difference color models are predictors used to reduce entropy. The fact is that, firstly, the color of each pixel in the three-component color model can be represented in form of coordinates by three linearly dependent vectors of any basic colors. Secondly, different image components display sufficiently similar geometrical spatial structure objects. An example of such similarity you can clearly see on the screen. Difference color models are used to maximize entropy reduction due to their intercomponent decorrelation. Therefore, they increase the efficiency of the application of the context-independent algorithm, although they don't directly perform data compression. For an ambitious decoding, there can be a maximum of two differences in the difference color model. The correlation coefficients between pairs of the components in RGB color model for different images can differ significantly from each other, and one of the components of such arbitrary pair with a strong correlation can be replaced by the difference with another component, if this will reduce the entropy in the further process of context-independent coding. Using component difference instead of component luminance of the RGB color model performs intercomponent decorrelation, just as predictors implement decorrelation between adjacent pixel luminance. When calculating the differences in the luminance of components in cases where the luminance values of the subtractor insignificantly exceed the luminance values of the reduced one, negative values of the differences are obtained, which when stored in unsigned 8-bit components of the color model are transformed into values close to 256 due to the overflow. And when the luminance values of the subtractor are slightly smaller than the luminance values of the reduced one, values close to the zero are obtained in the differences. This dispersion of color model difference values negatively affects the accuracy of prediction and therefore increases entropy. To avoid such dispersion of the values of the differences of close luminances, it's customary to shift them to the middle of the range of possible component values, as in another color model. If the individual components in the image were coded into separate compressed blocks, then the length of the entropy code of the difference of the components would be equal to the length of the entropy code of the opposite difference, and the following 16 color models would be alternative. Among these alternative color models for each image, we choose the one that provided the lowest entropy. But the luminances of the pixel components are stored consistently, and therefore the length of the entropy code of the difference of the components is not equal to the length of the entropy code of the opposite difference. As a result, the number of alternative differential color models increases from 16 to 49. All of them you can see on the screen. If we analyze the effectiveness of differential color models with the same reducibles or minuses, then their number will be reduced from 49 to 31. We are going to present the results of testing of our proposed difference color model selection algorithm for each image on the test set AST. This set contains both photorealistic and discrete tone images. To ensure the tests are conducted correctly, you can check the main characteristics of the images of this set. As you can see, different difference color models provide the lowest entropy for different images. We can see that on average for this set, due to the use of difference color models with integer coefficients, the compression ratio is decreased by 0.36. Moreover, about 19% of this decrease occurred due to the shift of the median difference to the middle of the range of the possible values. That's due to the consideration of alpha, the third line of the table 1. The effectiveness of difference color models differs first of all for different types of images. If for photorealistic images the compression ratio is decreased by an average of 0.98, and then for discrete tones images only by 0.01, since they have a low level of correlation between components. For image number 1, there was even a fallback to the RGB color model, as an alternative difference color models are reduced by predicting entropy code length by less than 1%. The choice of difference color models, not from the 49s, but from the first 31, with the same minuends and subtrahends, forms models with opposite components in 25% of the images, which significantly increases their compression ratio. On the other hand, this doesn't lead to a drastic acceleration of compression, because most of the time in the process of choosing difference color models is spent on forming a component frequency and their differences. In general, the use of difference color models significantly, on average for more than 13% according to Table 2, slows down encoding not only due to the need to choose such a model from among alternatives, but also due to the orientation to a context-independent algorithm that encodes individual literals. However, the time of image decoding due to the use of these color models is increasing by only tenths of a second, 9.3%, second row of Table 3, which together with significant reduction of compression ratio makes it possible to use them effectively in practice. While conducting the research, we came to the following conclusions. It's possible to reduce the compression ratio of images in three-component color models, not only due to the data decorrelation of individual components, but also with the help of intercomponent decorrelation by switching to different color models. Intercomponent decorrelation should be performed in such a way as to enhance the properties of the image used by the algorithm of present and direct compression of the selected graphic format, for example, to minimize the predicted length of the entropy code. The use of difference color models with integer coefficients in the process of progressive hierarchical compression of lossless images makes it possible to reduce the compression ratio of photorealistic images by an average of 0.58. To ensure the smallest compression ratio, a difference color models with the integer coefficients should be chosen from all 49 alternatives. In order to increase the efficiency of the application of difference color models with integer difference coefficients, the median differences of the basic components RG and B should be shifted to the middle of the range of possible values. For example, color models with a sampling rate of 8 bits up to 128. Integer difference color models provide significant improvements in the lossless compression efficiency of three-component photorealistic images in the format that use predictors, and may therefore be implemented in future standards level versions of these formats. In the future, with the aim of further reducing of file sizes of lossless compressed images in the process of progressive hierarchical traversal and speeding up decoding, we plan to increase the efficiency of using symmetrical and asymmetrical predictors by applying different color models with integer coefficients to image fragments. We are working on an algorithm for dividing images into large rectangular pieces with different adaptive difference color models by analyzing their median differences. Thank you for your attention.